Welcome. My name is Lina Musa and I am a product manager in raw milk testing segment at FOSS. This is webinar How to calculate conversion equation or so-called conversion table for BactoScan and BacsoMatic. This equation is used to convert individual bacterial count to colony forming units. Today we will cover the statistical analysis of collected data and calculation of conversion table. Thank you for joining me today. Let's begin. First thing you have to do is to collect the data which uniformly covers the whole range of interest and are representative of the routine samples. The test should be conducted at least in duplicates for both methods, routine standard plate counting and alternative flow cytometer. In our case, we will be talking about BactoScan. Initial evaluation of the data can be done after 200 samples, whereas for a robust conversion table, at least 600 samples in duplicates have to be analyzed. All collected data must be paired correctly and the units per microliter or milliliter must be noticed. In this example, data from the BactoScan are written in IBC per microliter. It's individual bacterial count per microliter. Whereas the data from Petri dishes are written in CFU per milliliter, colony forming units per milliliter. I have added already all data, but please note that all data presented in this example are for the training purpose only and should not be used in your calculations. So, as you may notice, the data from BactoScan and from Petri dishes are in different units. In order to proceed with calculations, all units must be the same. And according to standards, all data should have units the same as reference method. In this case, reference method is Petri dishes and data are presented in colony forming units per milliliter. Therefore, data from BactoScan have to be recalculated to IBC per milliliter. To do so, data from BactoScan must be multiplied by 1000. Here on the top, you can see highlighted formula how to do calculations. So if we will take, for example, first sample from BactoScan and first replicate, and we multiply it by 1000, we will get 14,000 IBC per milliliter. The same we are doing with the second replicate of first sample, multiplying by 1000, and you are getting 12,500 IBC per milliliter. To copy this formula for the rest of the data, just mark 2 cells calculated and drag it down. So now all data have been recalculated from IBC per microliter to IBC per milliliter. The next very important step in conversion table calculation is to transform all data to logarithmic scale. And why it is so important? As you might know, the exponential growth of microorganisms usually leads to a right-tailed distribution. But a prerequisite for statistical analysis is the approximation of a normal distribution of the data, and therefore the transformation of the raw data is necessary for approximation of normality. This is usually a logarithmic transformation. In the top scattered diagram, you can see the distribution of non-transformed data, whereas in the scattered diagram below, added data have been logarithmically transformed. And you can see the different, how the data are distributed. Now if we go back to the raw data, you can see the formula used for data transformation. So if we take first replicate from first sample of BactoScan IBC per milliliter, so you're typing logarithmic 10 and choosing first replicate. The same you're doing with second replicate. Please note that I am using IBC per milliliter. And the same we're doing with the reference method data, logarithmic 10, CFU per milliliter. And the second replicate, CFU per milliliter. Now we have first pair of samples from BactoScan and BacsoMatic transformed to logarithmic unit. To transform all data, mark the cells and drag it down. And here you are. So what we did so far? We have data, two first column from the BactoScan, first replicate and second replicate. In the next two columns we have data from Petri dishes, first replicate and second replicate. It is very important to have data in at least duplicates, and I will show you in a moment why. Further, we had data from BactoScan in IBC per microliter, and from Petri dishes we had data CFU per milliliter. To align both of them, data from BactoScan were calculated to IBC per milliliter. To do so, IBC per microliter have been multiplied by 1000, and we got IBC per milliliter. In order to have normal distribution of our data, all data have been transformed to logarithmic scale. When all data are transformed to logarithmic scale, we can do now statistical analysis. First of all, the mean value of each sample must be calculated. On the top you can see highlighted formula to be used for mean value calculations. So to calculate a mean value for first sample from BactoScan, type average and you're choosing two data, first replicate and second replicate from the first sample BactoScan logarithmic IBC per milliliter. The same you're doing with data from Petri dishes average and choosing first replicate, second replicate logarithmic CFU per milliliter. Now you have mean values from both BactoScan and Petri dishes for first sample. To repeat the same for the rest of the sample, mark the cells and drag it down. So now we have mean value for all samples from BactoScan and from Petri dishes. I have mentioned earlier that it is very important to have all data in duplicates because it is very important to check how well results are repeated on both BactoScan and Petri dishes. We see many outlier due to repeatability errors, especially on Petri dishes, on reference method, where many factors such as slightly different incubation conditions, dilution error, and or human error have impact on repeatability. The repeatability outliers on BactoScan can be due to improper sample handling. So in order to identify all data which are not repeated well and to delete them from further calculations, All samples must be tested in duplicates and repeatability outliers must be calculated. To look for repeatability outliers on the BactoScan, we have to calculate the standard deviation. And to look for repeatability outliers from the reference method, we have to calculate the absolute difference between two replicates. The differences in repeatability calculations is due to differences in technique. And according to standards, the repeatability limits for the alternative method, so in our case BactoScan, where technique is based on flow cytometer, is defined in ISO 16297. And it's saying that for total bacterial count in raw milk, the acceptability limits for the repeatability standard deviation is 0.09 log units for contamination level 20,000 CFU per milliliter. However, we have internal force specifications for standard deviation of repeatability, which should not exceed 0.07 log units in the range from 10 to 50 IBC per microliter, 0.05 log units in the range from 51 to 200 IBC per microliter, and 0.04 log units where bacterial count is more than 200 IBC per microliter. If you will look at the whole range, so 0.05 log units is an average. So this is for flow cytometer. But repeatability limits for the Anhor method, so it's Petri dishes, it's defined in ISO 4833, and it's saying that the absolute difference between the first and the second result should not be greater than 0.25 log units. So here you can see that for flow cytometer, we are looking repeatability standard deviation, and for Petri dishes, we are looking for absolute difference. So let's go back to raw data and calculate standard deviation for BactoScan results and absolute difference for Petri dishes results. And again, you can see formula highlighted on the top. So let's start with standard deviation. We are choosing standard deviation per sample, and then marking the two data from BactoScan logarithmic transformed, whereas for Petri dishes, we are choosing absolute different, absolute, and first replicate minus second replicate. So here we got standard deviation for BactoScan data and absolute difference for Petri dishes, data from Petri dishes. Mark both cells and drag it down to do calculations for the rest of the data. To identify outliers where the repeatability for BactoScan and repeatability for Petri dishes are above the limits, we should choose a function if, and then we typing the cell which we want to compare. The standard deviation from first sample 0.03 should not be higher than 2.83 multiplied by 0.05. 2.83 is a coefficient of repeatability limits, and 0.05 is a standard deviation of repeatability. So if standard deviation is higher than this calculated value, so we have outlier. If it's below calculated value, we leaving the empty space and pressing OK. To copy the same formula for the rest of the data, just mark the cell and drag it down. And here we have already one outlier. Let's mark it. So, do we have more outliers for BactoScan? Here is one more. We're marking it as well. So we had two outliers for BactoScan repeatability. The same function we are doing for the Petri dishes. So function if, and logical test would be absolute different, more than 0.25 log units. So if it's true, we have outlier. If it's not, so we're leaving the space and pressing OK. Mark the cell and drag it down. And you can see already that we have more outliers here. And we have to mark all of them. So now all outliers are highlighted. In order to proceed with calculations, I would recommend to mark all these calculated data and copy. Go to next Excel sheet. I named it calculation and do paste. Now we have the same data here, but what we will do, in raw data sheet we have all data. We will not delete nothing from here, so you can go back and to see which data you had previously. However, in calculation sheet, I'm recommending to delete the lines which has outliers, because we cannot work with the outliers, repeatability outliers. These samples have been done, something wrong happened, so it has to be deleted. So delete and shift cells up. Same doing. And we're deleting all line. When you're pressing delete and cease to be marked, shift cells up. So when this one line is deleted, all cells will be shift up. So we deleted all repeatability outliers. We don't have any highlighted cells left. Now the next step, we have to draw the scatter diagram. To draw the scatter diagram, we will use the logarithmic mean values from BactoScan and from Petri dishes. So we have to select cells, then going to Insert, Scatter Diagram, Dots. Let's work a little with the diagram to be it more clear. We can change the axis format. So we can see that it's starting somewhere around 4. So we can also add 4. And here I would choose might be 2.5. And we will type axis titles. On horizontal axis we have logarithmic IBC per milliliter. On vertical we have logarithmic CFU per milliliter. The next step is to add trend line. We can choose to display equation and display R squared, and the trend line should be linear. Move the formula here. So here how our data look now. In order to proceed, we have to calculate accuracy standard deviation, and the acceptability limit for this accuracy standard deviation SYX is 0.4. Let's see what we will get here. To use it, to calculate it, we're using formula STEYX. It's highlighted on top, and then we are using known Y scale. So known Y scale is average results of logarithmic CFU per milliliter from the reference method. And then we have to choose known x-axis, so it will be logarithmic IBC per milliliter. Press enter, and we have 0.32 is below than 0.4, so it's saying that our data are distributed in linear regression. Here we have to can do some calculations for the slope, and again we're choosing known y-axis, y data, and known x data. For the intercept, we are typing intercept and selecting data log CFU per milliliter. And log IBC per milliliter. And you can control if it's the right the calculations and the drawings was right. Here you have a regression line and the equation 0.8525 x minus 0.244. So 0.8525 is our slope, and we got exactly the same when we calculated. The intercept is minus 0.244, and we got the same when we did calculations. To check for microbiological reason outliers, the accuracy standard deviation multiplied by 2.58, so it will be our limits, standard deviation multiplying by 2.58, we are getting a value 0.8252. So now first we have to calculate estimated CFU. Estimated CFU is we will use IBC, logarithmic IBC from BactoScan data, and we will use this equation to calculate estimated CFU. If we will choose first sample logarithmic IBC per milliliter multiplying by slope and adding intercept. In order to keep this formula not to change, we have to add $sign, so we can drag formula down and it will be calculated for the rest of the data. So we got 3.27 logarithmic units. It's estimated CFU per milliliter. I can add per milliliter. Selecting the cell and dragging it down. And here you have calculated estimated CFU per milliliter. Next step, we have to find the difference between estimated CFU per milliliter and CFU per milliliter in Petri dishes. So we are looking for absolute difference. So we are selecting average result from Petri dishes and minus estimated CFU. Marking the cell and dragging it down. Now we calculated the difference between estimated and calculated CFU. Calculated CFU, it's average results from Petri dishes. So when we have estimated CFU and we have difference between estimated and calculated or counted CFU, we can look if there is outlier of microbiologic reason. Here is on the top, you can see formula. So typing if, and logical test will be if the difference is more than linear regression model. Again, in the middle, we're adding $sign, so the cells will be not changed when we're dragging down the formula. So if the difference is higher than linear regression model, then we have outlier of microbiological reason. Otherwise, we're leaving this space, pressing OK. So marking the cell and drag it down. Let's see if we got outliers. Yes, we have one outlier here, which we have to mark. One more. When we identified outliers of microbiological reason, this dataset have to be removed. So what we do now? We are writing down logarithmic IBC per milliliter, the mean value, and then we have logarithmic CFU per milliliter, the mean value. I'm just transferring this data here to be easy to see and to understand what is going on. So logarithmic CFU per milliliter. So basically what we have in column AO and AP is the same what we have in column O and P. Marking and dragging down. And here what we have to do, we have to delete the data which is without layer. And then begin marking the line so it will be very easy to see where outliers have been. So we deleted 4 samples from our sample set. And now again we have to draw a scatter diagram. We can copy this one and paste. And now what we will do, we will just change the data set. Serial 1, edit. And we have on X axis we have BactoScan results. And on Y axis we have Petri dishes results. So now we have scatter diagram. Just press on the scatter diagram to see which data are included. And you can see also that the formula have been changed. If I will zoom out like that. Here we have 0.8753 x minus 0.3783, and in previous scatter diagram we had 0.8525x minus 0.244. So now again we have to calculate STYX standard deviation, and we call it selecting the data from Petri dishes and then the data from BactoScan, and again we have very nice standard deviation, which is below 0.40, and before we had 0.32. Calculating the slope. And calculating the intercept. So now we have slope, intercept, we have very nice linear regression, and R squared is more than 0.7, so it's 0.7851. So we can look now for minimum and maximum value of IBC and CFU, which will be later on key into BactoScan. To look for minimum IBC value, we are typing minimum and we selecting IBC per milliliter, data from BactoScan. And the same we are doing with the maximum value. Because we need 2 points, we have linear regression, so 2 points is enough for our conversion table. And here we have maximum IBC per milliliter. In order to calculate logarithmic CFU per milliliter, because we have logarithmic IBC per milliliter, now using regression line equation, we can calculate log CFU per milliliter. So it will be slope multiplied by log IBC per milliliter and plus intercept. The same we're doing for maximum value, slope multiplied by maximum value and plus intercept. So we have logarithmic values IBC and CFU per milliliter. However, into BactoScan, we have to key in normal data. So we have to transform from logarithmic to normal data. So we're using formula 10 and choosing log IBC per milliliter. And we're getting 10,724 IBC per milliliter. Just drag the formula to the side so you will get CFU per milliliter. So 10,724 IBC per milliliter equal 1,410 CFU per milliliter. And also drag this down so you have minimum and maximum per milliliter. To recalculate per microliter, so we have to data per milliliter divide in 1,000 and you will get 11 IBC per microliter equal 1 CFU per microliter. And then 22,000 IBC per microliter is equal 149 CFU per microliter. So these numbers have to be keyed into BactoScan and used for IBC recalculations to CFU. Why do we need to calculate standard deviation for BacsoMatic and the absolute difference for standard plating method? All collected data should be evaluated for validity. According to ISO 21187, replicates exceeding the established limit for repeatability should be excluded. Repeatability for total bacterial count on BactoScan or BacsoMatic is expressed by the repeatability standard deviation, which should not exceed 0.07 log units. This is for specification. However, ISO 16297 saying that it should not exceed 0.09 log units. Repeatability for standard plating method should not be greater than 0.25 log units of the absolute difference between two replicates. What to do if accuracy standard deviation is higher than 0.4 log units? The acceptability limit for the accuracy standard deviation should not be more than 0.4 log units. If it is more than 0.4 log units, evaluate the sample collection and handling and instrument performance. Many factors may have impact on high accuracy standard deviation. For example, improper sample handling, too little samples included to the calculations, or very big variation between seasons. Will the conversion table change if, for example, laser or other mechanical pad will be replaced? No. Only factors such as seasonal variation, sample handling, methodology, or used chemistry, and so on, may impact changes in conversion table. How long it will take to collect data and to make a robust conversion table? It may take from 6 to 12 months. BactoScan. Will the conversion table be valid if we change from low sensitivity to high sensitivity? Yes. However, you may need to add data in lower bacterial count range. How big the difference will be if outliers will be not removed? It will depend on how many outliers do you have and how big distance is from the rest of data. Outliers are influential if they have a big impact on the regression equation. When data set is very large, a single outlier may not have a big impact on the regression equation.